Hi, welcome back to part 3 in this series on building a virtual console with AI. Um, well done for sticking with me so far. This first part is quite dry, I guess. It's always kind of a 8-bit hardware emulation. Not even doing emulation yet, but just this kind of bits and bytes flying around. I guess it's a little bit dry, but hopefully still interesting. You might remember at the end of the last episode, we basically got a program running, and we can do a quick recap. I hope we've got one running. Yeah, I've got one running here. So memory fill, we were able to load a program into memory and then run it and see it running in our sort of hex viewer, see registers changing and see content changing. We can see the values appearing in the top there. We didn't dig too far into it. However, we particularly didn't dig into actually the program, how the program was put together and what was happening. We don't have at the moment what's called an assembler. And what an assembler does is it takes basic instructions, a slightly higher level language than the bits and bytes that we're seeing on the screen here, and converts them into those bits and bytes. So the LLM actually did that for us. If we go back to the code, you might recall we had the CPU example that we built. I have done some slight reorganization just to introduce a secondary source folder under here, so that the package.json isn't muddled up with it. That wasn't great, but I've tidied that up a bit. But that's the only change I've made. If we look in the programs.ts file, which is what I've got open here, these are the programs that you can pick and run. And you can see that essentially what's happening is we're building up, arrays of bytes very painfully. But actually, back in the day, as it were, I never had to experience this, fortunately. But prior to assemblers and things like that, people would actually, poke the bytes into the system. If you look at people using something like the Altair, one of the early microcomputers, they're flicking switches to set the bits and pressing a button to kind of push that into memory, and they're essentially hand assembling a program, which is what's happening here. The nice thing is the LM assembled this program for us based on our CPU spec. We didn't have to do it, thank goodness, because it's quite painful and error prone and frail, really difficult to do. Writing assembly, which we will look at in a minute, is also quite difficult to do, but not as difficult as this. So what we want really to write programs at a low level on this kind of hardware is something that will take a slightly higher level program and convert it into the bytes. And a program like that is called an assembler. A question worth addressing is why not use a language like C, or back in the day BASIC was very popular on the 8-bit micros, and you certainly could use BASIC and you could use C. I actually had a C compiler on my BBC micro, which is where I first learned C. The problem is that the machines were so slow and the memory constraints are tight that to do, write a game, for example, you would quickly brush up against the limits of memory and processor speed. So even if you've got a C compiler or something actually doing a compilation for you, the code was not as efficient as hand-assembled code. People would run a compiler on a machine that was also incredibly limited in space and speed, so it couldn't do the kind of crazy optimizations you might see today if you had something doing that. C compilers, things that jittered languages do is amazing. None of that was on the table. So to really make things fly, you had to write this really low level code, and people wrote assembly, and that's what we're going to look at here. So you write assembly and it gets translated into bits and bytes. I have done a little diagram that hopefully will make this clear. Yes, so here's my diagram. Essentially, on the left is some assembly language for our CPU, and these are the opcodes and things that we've been looking at, the registers in the CPU specification. And on the right hand side you can see the actual bytes, the machine language that we want to end up with. And in the middle what we have is something called an assembler, and that takes the stuff on the left and converts it into the stuff on the right. And it introduces various niceties. So we've got, for example, this main here as a label, starting label. We don't really use it again. It's a bit of just a readable marker. But loop, for example, down here you can see we keep incrementing our counter, and eventually we do this comparison, and if that's not 0, we continue, and we do that by going back to loop. And essentially what's happening is the assembler is tracking where loop is in memory, based from the start of a program, so that you don't have to, if you look at the code, if we were to look at the code in the machine code, in here somewhere will be a branch instruction. It's just so difficult to see. Branch, there you go, branch, and it's kind of manually tracking loop program. But if you didn't have something like this to express it in, imagine doing this by hand with the bits and bytes. You'd have to calculate how many bytes to go back. Just really painful. So that's what the assembler gives you. It gives you this, pressing the wrong button. It gives you this this tool for operating at a very low level, but with some conveniences. They were, back in the day we didn't all of this, but you can do things like additions of constants in them, put comments in there, various sort of niceties that just help you write more complicated programs. If you want to see what I would class as some serious assembler, the BBC Micro site we were talking about earlier. Let me just go to it. BBC Elite, I always forget what this thing's called. The Elite. Here we go. The Elite site we looked at last time. If you go here, you can start to. Am I looking at Lambda? No, it's fine. I'm looking at the right thing. So let's just find something. Subroutine. Let's find a subroutine. Let's copy protection. Text tokens. Main loop. Okay, main flight loop. And I studied this a lot to convert Elite into TypeScript. That's a really simple one, but if we keep going, you can see this is more serious assembler. Now, the chap who did this, Mark Moxon, he's broken this out nicely into little modules and chunks. But this is essentially what you'll be writing on the 8-bits. This is what David Braben and Ian Bell wrote to write Elite. This is their source code, very nicely annotated by Mark Moxon on the right and organised so that you can make sense of it. So that's kind of an example of what I would class as serious assembly language. It's extremely obtuse. And I am in awe of Mark, who was able to decompile all this, disassemble all this, and make sense of it. That's one heck of a feat. Goodness knows how long it took him to do. I've never spoken to the chap. I think we exchanged a message on Twitter at some point, but I've never spoken to the chap, and I've no idea how long it took him to do, but it must have been quite arduous. In any case, that's assembly language, and we need to construct this assembler so that we've got a way of assembling some code. Else we're going to go crazy. I mentioned at the start, I've actually written a spec for this. In the next, probably the next episode, I'm not going to pre-prepare a spec. We're going to do something UI focused, and we're just going to do it all live. But some of this involves quite a lot of back and forth to get the spec in the right place. And like I said before, I don't think people are that interested in watching me do that for 4 hours. So I've pre-prepared some of these things. So again, I've got a spec in the tools folder, assembly.md. I was quickly refreshing myself on what this said. I had a read of it earlier. But a good question is, how did I construct this? How did I put the spec together? I put it together essentially by constructing, unfortunately I don't have it, but I constructed a prompt for the LM to help me build the spec. And I basically stated the things I wanted to do. I put several of these things in this list of contents here. I didn't put all of them in, but I said I want to cover at least these things, so like addressing modes, labels, various things that we'll see I asked it to do. But I also said, I want a powerful assembler. I gave it the CPU spec, and I said, can you work on this, please? And we backed and forth over it a little bit. Two-pass assemblers, this was quite common. for forward reference, 2 bytes assembler for forward reference resolution. It's really awkward if you can only reference backwards. So early in the program, that becomes quite difficult to deal with. It's something that's so low level. So 2 bytes assembler, it'll go over it once and figure out where all the markers are, and then let you call forward and backward, which just makes writing the code an awful lot easier. Source maps, symbol tables, they'll help us later when we come to build a debugger. We will build a debugger for this system. Output into binary machine code, input plain text assembly source code, fine. Some stuff is case sensitive, some isn't. Essentially the labels are case sensitive and nothing else. Everything else is case insensitive. We're at white space, I'm commenting on white space. We need to do various addressing modes. Each of the addressing modes needs a syntax. Actually, we kind of captured a lot of this in our CPU spec. So it's really a reiteration of that for the assembler. Relative labels, and then some directives. So some stuff you need to be able to tell the system to do things. These are really common things. So .org, where do you want to load the program into memory when it loads? Not in some ways that could be a bit optional, because we could have this thing just output a byte array. And actually, when I do the import, I might ask it to do that. Just essentially just output the byte array. But then we'd have to patch up the references and things. So you think about it's going branch to this point and branch to that point. It's doing that based on memory locations. So you would often assemble this into a place in memory, and the starting location then is the offset for all the jumps. None of this is particularly dynamic. It's literally all about the bytes that end up in memory, which is quite strange today. in today's days, it's quite a strange thing. It's quite strange to me. I mean, I used to work with some of this, and it's quite strange to me now. And I talk through it, and I'm like, oh goodness. I don't know if it's a sort of flashbacks of pain, or just astounded that we made things work like this. And I mean, I wasn't very good at making this stuff work, but people did amazing, stunning things with this. It's quite impressive. In any case, we want to reserve bits of memory and be able to load data into memory. So we've got some things here. On the BBC, my memory is, for example, with slightly different directives, that was something called equa, EQUW as I recall, and that will let you load a word into memory, 2 bytes. equb would let you load a byte, but we've got a slightly different way here than BBC. Strings, let you put strings into memory, they'll go down into ASCII basically. And on we go. Numbers, hexadecimal numbers, binary numbers, very useful to be able to put binary patterns into memory. And what I'm going to do when we've got this thing up and running, because I'm going to forget this, this is stuff that's quite hard to keep in your head. Back when I was writing this stuff, I'd be forever in books and manuals. So I'm going to create a cheat sheet for us. I say I'm going to probably get the LLM to create a cheat sheet for us, but we're going to end up with a cheat sheet, so it's a bit easier to do this. And also we'll build out a decent quality editor that helps us do this as well. The idea is that at the end of the project we'll have kind of modern tools that let us work with these sort of retro assets and languages, which should be quite fun, I think. Assuming I can make it all work. Could all end spectacularly in failure. We'll see. We'll see how we get to. But we'll learn something either way, so it's all good. Labels. We talked about labels, marking places in memory so you can go back to them. Label references, how do you call them? Expressions, I alluded to this earlier. This isn't so you can write if then, if this, do that. It's to let you do things with constants, basically, do compile time things. I mean, essentially, you could think of an assembler as a compiler in many ways. It's just an incredibly primitive and incredibly low-level one. Assembly process, fine. You say it collects up the symbols, marks where they are, so you can refer. When you before referencing, it knows how to find the symbols. So that's all calculating. The first pass, it's figuring out how big all the opcodes boil down to, so you can calculate the instructions. And on the second pass, you're basically resolving those references into the real memory addresses. As I say, I might have a go. I'm not sure I'll do this episode or not, but have a go at making this thing relative. Let's pack up a relative kind of system. I just have to think about how I do that, but that might be quite handy. Pardon me. Sorry, I had my dinner. It's the evening. It's repeating on me. Program can define. That's how it tracks our way through it. Instruction encoding. We know about this. This is the packing that we've seen. We've seen on the CPU. We want it to pop out in a uint data array. Yes, that's what we want. One machine code bytes. Yes, that's what we want. Okay, listing file, error handling. We want to tell us about sensible errors. Fine. And I'm going to ask it to make this essentially, in the first instance, as a single module that exposes a single function, assemble, and we pass into it some assembly, and we get out of it some machine code and or some errors, and the machine code will be in one of our memory maps. It's got an example here. Look, it's compile this example. I didn't ask it to compile that example, but it is that's a sensible example. And you can. This is actually, I guess it's probably built from its. This was probably at the end of a long conversation with Claude, and I would have been talking about rendering and graphics at some point as I worked on memory map. So it's done something about clearing a screen and VSync and things like that to VBlanks, which we will when we get to that point. Which actually we're going to come to quite quickly because I think that makes it exciting and come alive. We'll start to. Better implement things like this basically, which should be really interesting. So I'm going to do one of my normal things, which is in here, write a assembler impl.md, and I'm just going to copy one because I'm going to ask it to do some of the same things. Just grab some bits. Assembler implementation, Weaver files, TypeScript guidelines, and the CPU spec, CPU implementation, source/console. I also tidied this up so it's a little bit neater as well. Yes. It'll find the memory map if it needs it from the CPU implementation, so I won't bother specifying that. /specs /tool/assembler.md. Okay, and then your task is to implement the assembler as defined in the specification. The output should be a single contained module I'm actually going to put this in the console because it's kind of going to live with the console and get reused in lots of places. I may end up with some sort of shared folder later, but I think I will try and avoid that for the moment. It's going to be quite tightly tied to the hardware. I mean, no, we're not implementing it as something with we're not implementing it as something accessing the file system. We're just going to have it read the code in as a string and say return the assets. I actually need to return the symbol maps and things. So we'll ask it to return a structure containing the memory map and the symbols and debug information, etc. Exported function called assemble. We should take a string containing the assembly code and return a structure, an interface, a type, that include the machine code in a memory map and associated artifacts such as source and symbol maps. For example, function assemble code, assembly code, string colon assembled artifacts. Read the implementation and then ask me any clarifying questions. Usual kind of thing, but we've done a couple of times now. So let's go to Claude. I have Claude open, that's handy. It's in the right folder. Read the specification that you can find in specs/implementation /assembler-impl.md. Hopefully I've typed all that in correctly. It's a lot easier typing that correctly than the many lines of code that are in the assembler and the CPU. And by the way, I did review the CPU. I've not reviewed every single opcode. It looks okay. The one thing I did find, and I'm going to correct the TypeScript guide actually, I should have done that before we started, is I'd asked it to use the hash syntax for privates, and it hasn't used that. But on looking at it and asking the LLM why it hadn't used it, I left it a degree of ambiguity as to when it should use it, and also I suggested using constructs that in places where it couldn't use it. So it's actually quite new to me in terms of using that hash syntax. I've not used it very much at all. So I'm going to remove it from the TypeScript style guide and just let it, work. Let it just not do that because I don't think it's helpful actually. Okay, so we've got some questions. Let's. They're good questions, I can see already. Let's see. Switch this to Markdown. Okay, memory map format. Yes, interesting question. So I've been talking about this, haven't I, in some sort of roundabout ways. We're going to get it to give us the first answer, and we'll just give us the chunk of code starting from the first .org address. So if there's 10k of code, we'll get a 10k memory map, but we have to know to load it into the same space that the org address represented. So I'll say 2. So if there's multiple org directives, do we want to let it do that? For now, let's say don't allow. No, actually, we will allow this because we might want to. We've not really talked about memory banking, but I can see we might want to do some interesting things. So let's have it represented as separate memory segments. So we probably get an array back. A structure that includes the memory map and the starting address for that memory map. So we should get an array back. Those things, okay. We wanted to use a CPU spec. I think that's me iterating one out of sync of the other. So I left it to Use the CPU implementation and CPU spec. Yeah, I think I've updated the CPU spec, and it looks like I forgot to update the assembler spec. For a register pair inductor thing, so we're going to enforce it in error. So you can't do sort of R0 and R4, you have to do R3 and R4. Good question. Should expression be evaluated as fed to integer for checking 16-bit address size value something else? I'm not sure. We can change this later. Let's go with but yeah, store them. So if you've got a label, we've got a concept of like global labels and local labels, almost like local variables, and we'll have them as fully qualified names. So we can always track them in a simple table. So I'm going to take those answers and I want to put them back into Claude Code. You can see from this that I've not been in this world for quite a long time, so there's a lot of stuff that is challenging and uncertain to me. But that's partly why I figured it might be an interesting thing to tackle, because if I kind of had all the answers, probably a bit boring. So we'll see. And my general thought with this stuff is, and my general approach to development is, and hopefully this isn't another heretical view, but it's only code. It can only go wrong so far. At least this kind of code, it's not controlling robots. It's not controlling physical machinery. We can try things, test them, undo them, do things a different way. We can be quite playful with this, which is great. It makes it fun. If we were, developing a system that had real world implications, we wouldn't be able to be quite so playful. In fact, when working on, I work on, agentic AI at the moment in the day, and there's a lot of focus there on running experiments around outputs and validating outputs. It is not playful. It is a real system. It's not a virtual console. So it's a very different way of working with these things. And I think you have to, again, I was talking about value in the last episode, you have to understand where the value is and what's important, what the constraints are. There's no real constraints on this series. We can play around in a commercial environment. That often isn't the case, and there are all sorts of constraints, and you have to work with them. These tools, as before, are not magic answers, and the less playful it is, the less magic they are. But we can be quite playful in terms of our ability to experiment and just undo and change things later. It doesn't really matter. So we'll continue to do that. That said, you can see I've spent quite a bit of time on specifications. This isn't I despise the term, but it isn't a vibe coding project, at least not this part. We've got some definite outputs, some definite things we want. I'm going to do my normal pattern of letting it make edits, because I'm going to come back and we've got a commit we can always roll back to. This isn't, I want some specific outputs out of this, so it's not, we can't be quite so freewheeling. In the next episode, we're going to start building out some UI in React, and I think we'll be a lot more interactive with the LLM than we have been here. So I'll probably write a bit more code by hand. I'll ask the LLM to help me with stuff. I might use the in IDE chat kind of more than I have. I haven't used that at all yet, but we'll be a lot more interactive in the next episode. while we build out UI. I find that it's just, I'm less wedded to how it should be, so we can be more interactive there. So it's whirring away. Feel free to skip. I can only talk for so long. I'll try and remember to put a chapter marker or something in so people can skip onwards if they want. Because this might take it a little while. It's got a big job to do. Okay, we're back. You can see I'll probably cut a bit out before we got back here because that was quite a long task, and I can only prattle on for so long. I was descending into dribble, so you can see it's finished and it's left us with 2 failing tests. I'm going to, before I answer that question, I think I'm going to ask it to make the fix. Again, we can always roll back, but before we do, I'm going to go and look at what it's done and see what we think of it. It's going to be quite. I'm not proposing we review it all here. We'll have a quick look at the test, quick look at the assembler, and see where we are. Interesting, it's not used for NOP. It doesn't need extended NOP. That's why it's not really used. Okay, fine. Okay, assembler error, memory segments, source map entry. Okay, that's the thing we asked it to return in fluffy English language. Source map entries, address, line number. Okay, that's tracking the address of a machine code back to the line of assembly. Symbol table, that's going to be the labels and the line numbers. Assembled artifacts, yes, segments, memory segments, symbol table, source map. Any errors? Okay, great. It's bold and took it up. You can see this is a lot of code. I mean, it's just generated a lot of code for us. It's interesting that there's a bunch of unused code. Okay. I find sometimes as it iterates, it leaves debris behind, so it will probably clear out some stuff. But let's see what it looks like. Keep going down. Yeah, I've seen this sort of thing before where it's iterated, and it's left things behind. And yes, that's not great, but humans do that too, so I'm not going to get too hung up on that. Okay, that's the expression evaluator. That, I suspect asking it to do expressions added quite a lot of code to it. Yeah, quite a bit, look. Okay, line parsing. Okay, 0 pages address. Okay, parsing out. It's all parsing. Okay, and this is where it takes an opcode and converts it into the bytes, into machine code. Okay, it makes, I'm not really reading it, but I can see at the top what it was doing. Okay, so the 2 passes. Pass 2 will be, pass 1's like doing most of the work, and pass 2 should be patching up and generating the code. Okay, fine. There's not the same somewhere, so then the exports at the bottom. Okay, interesting. So it takes the assembly code, returns the assembly out. Okay, so it looks like it's doing what we'd hope. Let's have a look at the tests, see what it's done as tests. Okay, so it's doing some basic assembly of simple things and making sure that they, compile correctly to the right things. That's pretty sensible. I'm curious to see what it's done with branching as tests. Here we go, branch instructions. Okay, so it's a forward reference. Okay, and it's checking that those things work. Okay, so it seems to have written a fairly sensible set of tests. Okay. We'll run them, but not until we've unpicked this question it left us with. So let's just go through this again. For a 2-phone test to local label resolution. Oh, okay. So as it goes. Okay, so we can't actually reference, so we couldn't, so as it stands, we couldn't let's pull them from a branch, use a sensible syntax, you couldn't. Okay, oh well. Funnily enough, I nearly wrote "don't change the code." Claude Code is quite eager to change the code for you. I found, and if I ask, it's not great at asking it questions. It tends to answer by making the change. I wasn't too bothered. My next thing was going to be, can you make the change? So I kind of have this debate in my head. It's strange that it did all the other work and left this, left that as an overhang for us to talk about with it. Given the body of work it did, it's strange that it kind of left that, fairly small fix that we just saw to the end. Again, I've no idea why, but yeah, it's interesting. It's often interesting working with these systems. Okay, and the tests. Great. A test pass. Let us go into. I might just need to kill the server. I'm going to go into my other thing here. It's quite small, isn't it? Yeah, it's quite big, so we can see that one. Fine. Let's exit the example. Let's go into console. What was it called? npm run test. Let's just see it run all the tests. Great, so everything's passing. Okay, so I'm going to do a commit at this point to create another checkpoint. I mean, we don't yet know if this really works for real, and that's going to take a little bit of time to establish. But it's pretty impressive it's generated this that quickly, I would say. I mean, I find it pretty mind-blowing. Let's push that up. Okay. The way one way is I'm going to test this, and hopefully a way that demonstrates it's worked or not really quickly, is I'm going to ask it to, can you replace the hand-rolled bytecode in source/, examples / CPU example / programs.ts with strings containing the programs in assembly language, and then use the assembler to assemble them. Update the surrounding code so they get loaded correctly into memory if required. So we're going to ask it to undo that hand-rolled assembly in our example program, this thing we were looking at earlier, and we're going to get it to put in some more, hopefully, human-readable code. Let us see. Let's see what happens. The voyage of discovery continues. I think I said I'm going to cut out a chunk of watching Claude build the whole assembler. Quite a bit of time has passed on my side of the video, so we'll have to call it an end of this session soon. Else I won't sleep because if I code too late at night, I can never sleep. My brain starts whirring. So if we get this working, we'll probably stop there and then come back to it in the next episode. And again, what I will probably do is review it offline, and if anything looks dodgy, we can talk about it. If not, we'll continue forging ahead. And we'll soon find out if the assembler's working or not, because we're going to start writing some more interesting code once we've got an editor on the screen and can actually, do something that isn't like pulling teeth. So yeah, it should be a lot more interesting. And people might notice I've got a Claude, I think Pro Max, whatever they call it. I've got that subscription of Claude. I found actually the normal personal subscription was pretty good. It got me a good few hours of usage, but it didn't. I'd start to run out of quota if I used it pretty continuously like this. So I upped my subscription to the, I forget what it is, the Max. Can't remember what we call it, but to that. So if you're doing really intense stuff, you might find that's the level of spend you require to keep it going. And of course, with this stuff still being pretty VC backed, we don't really know where the true cost of this stuff will end. On the one hand, the models are getting more efficient to run, and we're going to use a locally hosted coding model in this project in a few episodes' time, hopefully. I don't have the exact schedule. I do have a plan, but I don't have the exact schedule. But we're going to use a locally hosted LLM to do code. They're getting smaller, easier to run, but they're VC funded. They're funded on the promise of future revenue, essentially future profit. Where's all that going to land? I don't think we really know. So what the true cost is, probably open to debate. And if the bottom drops out of the bubble, if indeed it is a bubble, and I think it's very likely it is a bubble, so much money's been pumped in, there's going to be some carnage. Again, what does that mean to the cost of these systems? We'll find out. Hopefully it's not too unpleasant finding out. If you're around in the .com crash, like I was, that was not fun. Nor was the 2008 crash, and it would not be good to have another one of those. We'll see where it all ends. In the meantime, we can have fun building things like this. I didn't think the memory filled program was the one it's tripped upon. That was probably the simplest program. I think you're about to hear my dog. There's somebody within 200 metres of a house, so she's letting me know. All 5 example programs now passing. We had 10. That's not exactly reassuring. So this is an example of where we might need my my commit strategy to undo things and try again. Let's have a quick look, see what's in our program.ts file now. Doesn't look changed to me, but maybe there's something changed in the source. Let's just close things down. Dev kit examples programs.ts. It doesn't look to have changed anything. That's very strange. Let's put them under examples here. Look, that's very strange. Okay, so there's a great example of it not working. It's gone really wrong, and it's going to be difficult to scroll back up in code because it did so much work to see what I wrote exactly. But I was sure I was pretty specific, and it's still not quite got that right. It's gone a bit mad. It was built as a sample program, but rather than update the program in situ, it's created new programs. So I'm going to delete this. Yeah, we don't need that. Okay, it's not touched anything in there. So what I'm actually going to do is right. Okay, so I've written this. I've been very clear. I suspect the previous context that it's got above has misled it into thinking we're still working in whatever location. You noticed probably in the last episode I shut Claude down a couple of times and reopened it, and that was me kind of resetting it. So let me be a bit more specific. I've reopened Claude. Can you press the handle bytecode? Update the surrounding code. In CPU in source / console / source / assembler.ts to assemble The entry point is the assemble function. Update this running code. I'll be more specific here in the source/examples CPU example / project update. We handle bytecode. All your changes should be within source/example/cc example and its subdirectories. So we're going to just try and lock it into this this part of the system and see what it does now. I did say this series would be warts and all. It's definitely not an advert for Claude. It's like I gave it the wrong address, but it's found it. Okay, fine, it's found it. I typo in my spelling, typo in my path. So let's see what happens now. Okay, this looks a bit more promising already. Yes, we're going to make edits. This does look more promising. I think the context that it already had in terms of its previous conversation itself, its previous changes, a thing that it's already kind of got in its working set, had kind of confused it. And I find if I'm using like JetBrains AI or Copilot or whatever inside an IDE, I find myself doing new chats and things at kind of like what seem to be strategic moments to me. And that's really me thinking, actually, I don't want you to remember what you did before. I don't think that would be helpful. I want you to just do something again. And that's why I was closing Claude down in the last episode, and this time I didn't. I didn't think I would need to, but I was wrong. And maybe my clearer prompt would have helped, giving it more sort of guardrails around it. Would have helped, but maybe not. In any case, that's an example of it going wrong, which is hopefully helpful. And that'll happen several more times in this series, I'm pretty sure. It looks more promising. It's doing more, you can see it removing things and adding the things in the place we would hope, which is good. Again, I'll probably cut this here and go to the end, hoping that it, I'll edit this out so that you're not left looking at a screen updating. Okay, so it thinks it's done. Let's find out. Let's give it a try. Okay. Better. Examples. Well, that looks pretty good. It's doing a memory fill. You can see it's filling the memory as before. So it looks pretty good. Let's have a look at the code. Okay, programs.ts. Okay, great. So our crazy hex, our crazy byte loading and pushing has been replaced with some assembler, like we were looking at the start of the episode. Stuff you can vaguely make sense of now, and Handley's commented it, so that helps us. It looks like it's done sensible things. Let's try another program. I did try all these the other day, so let me just go back. I know I tried XOR Cipher, so let's see if that one works. Great, that's working. Let's try count to 10. Okay, 1, 2, 3. Great, so this has done a pretty decent job on the second attempt. As I say, restarting Claude, clearing out its previous context. I don't know if I ever tried simple sort. I'm just curious now. Does simple sort work? So there's 4 values at the top there, 42, 15, 89, 33. Does it sort them? Let's see. Swapping the look. Okay. Great. I mean, that worked. Let's put them in descending order, and it should decide it doesn't need to do any more work and finish. I hope. I can't actually manage one. Yeah, finish. There's a knob. It's finished. Finished. It worked. It's sorted. So it's converted the. I think I tried them all, but we can always go back to the commit if anybody's interested in the tag. I've been tagging them. Yeah, so it's essentially taken all that whole bytecode, and if we go to GitHub, we can see the horrendous. I don't use Visual Studio Code very much. I've said before. I think you can see we've gone from carnage to to something sane, or sort of sane. I mean, I'm sure to people today, the idea of writing a program like this is crazy. It was pretty crazy back then as well. That's how in all people could do it. But yeah, I think that's probably enough for this episode. I'll do a bit more review of. I mean, I didn't review it much at all. I'll have a review of assembler.ts sort of out of episode. I'm going to look for any obvious bloopers. I'm not going to be massively forensic on it. I'm going to look spot check and look for patterns. Mostly because of the project context. It's a fun project, and we're going to do things in coming episodes, but we'll test it further anyway. So that is what I'll do. There's probably some bits you found cut out this episode. That's me just trying to save a bit of time because there was a fair bit of screen watching. If you want screen watching, I could consider leaving that in and chapter markers and things. Let me know in the comments. What you would prefer. But thanks for watching. Episode 3. Great. It feels to me like we're making great progress, and it's going to be interesting to see where it goes next. Thanks for watching. See you in episode 4.